Last time in phase equilibria, we finally had an example problem where I showed you an application of how you would use the modeling approaches that we've been learning to be able to predict the PXY diagram for a specific set of experimental conditions. Importantly, I want to point out the fact that last time the data was for the specific temperature of 303.15 Kelvin, and the parameters that we fit to that data was then specifically for that temperature as well. So the main question I want to ask in this video is, what about other temperatures? Other T's. So in other words, if I were to now change the temperature, so let's say I wanted to investigate 320 Kelvin, would I have to run a set of experiments at that temperature as well and fit the parameters again? And would those parameters be different, or can I do other approaches? So how do we go about modeling the temperature and the pressure dependence? So I'll also say, what about other P? Even though for a PXY diagram, P is varying for a specific temperature, I might want to do a TXY diagram for varying pressure as well. So there's a couple of different ways we can handle this. The first one would be to choose a model that has built-in temperature dependence. Approach number one, choose a model with built-in temperature dependence. I'll put or P dependence. As I'm going to point out, and I'm kind of spoil the point of this video, pressure doesn't matter a whole lot. Temperature matters a little bit. T or P dependence. So one example of such a model is called the Wilson model. And so this would be in lieu of the Margulies. So Margulies does not have this temperature and pressure dependence. So I'm going to put that in parentheses. Margulies does not. So we have to choose a completely different thing. And I said that there's many different models for these activity coefficients. I mentioned the Wilson is the third one that we'll talk about in addition to the one parameter and the two parameter Margulies. So the Wilson model goes like this. All of these models are written in terms of partial molar excess Gibbs free energy over RT. And remember, this is the parabola that we fit with the one parameter and the two parameter Margulies. Wilson is a little bit more complicated. It's minus x1 times ln of x1 plus lambda is the parameter. Lambda 1, 2 is parameter 1 times x2 minus x2 ln times x2 plus lambda 2, 1, x1. So this is a two-parameter model as well. The two parameters in this case are the lambda 1, 2 and the lambda 2, 1. I don't know why, but when they label these parameters, oftentimes they like to do subscripts and they flip them around. You can look at this like the A's in the Margulies models. Now you may look at this and say, well, where's the temperature dependence in this? I will show you in a moment after I talk about the activity coefficients. In order to obtain the activity coefficients, you'd follow the same approach that I showed you in Friday's video, which is you would say that the ln of the activity coefficient, so I'm just going to do ln of gamma 1, is equal to the partial derivative of ng e over RT with respect to dn1 at constant Tp and n2. So once again, you would plug this whole thing in, you'd take the partial derivative with respect to n1, and then that would obtain your expression for the activity coefficient. I'm not going to show you that derivation. That one looks like it is a lot of sloppy math. The end result for the activity coefficients of the Wilson model, I will write them for you here. ln of gamma 1 is minus ln x1 plus lambda 1, 2, x2 plus x2, big parentheses, lambda 1, 2 over x1 plus lambda 1, 2, x2 minus lambda 2, 1 over x2 plus lambda 2, 1, x1. All right, once again, I'm skipping the derivation. I'm just going to write the other expression. All right, so there is the expression for the second activity coefficient as well. Once again, I'm skipping the derivation. Very long, involves a lot of math. Don't want to make a mistake. The way that you get this is, again, you plug in this expression for GE over RT into this equation for ln of gamma 1, and you evaluate this for the partial derivative with respect to n1. Same thing for the analogous expression for ln of gamma 2. Then you're taking the partial derivative with respect to dn2. But importantly, for your activity coefficients, these are your two equations that you would use. Now, where the temperature dependence part comes in is because these lambdas are actually not static parameters either. There's temperature dependence built into these. So the expressions for lambda are as follows in the Wilson model. Lambda 1, 2 is equal to molar volume of component 2 divided by molar volume of component 1 times the exponent of minus alpha 1, 2 over RT. And similarly, lambda 2, 1 is equal to molar volume of component 1 over molar volume of component 2 times exponent of minus alpha 2, 1 over RT. So in these equations, alpha 1, 2 and alpha 2, 1 are the actual parameters. So alpha 1, 2 and alpha 2, 1 are temperature independent parameters. So when you're modeling the Wilson, when you're modeling with the Wilson equation, what you're actually doing is you're fitting the alphas, and those alphas are going to be the same no matter what the temperature is. So same value, no matter the temperature. And then you're using these alpha values to plug into these expressions to find what the lambdas are. So lambdas are changing depending on the temperature. So if you do an experiment at one temperature and you figure out what the lambda is, you can use this expression to figure out what the alpha is. And then when you change the temperature, you use that same alpha, you update what the temperature is there to find the new lambda 1, 2 and the new lambda 2, 1, and then you plug it in to your model. So once again, that is approach number 1, which is when you're doing the modeling, you simply choose a model that has a built-in temperature dependence to it. Approach number 2 is to evaluate what the pressure and temperature dependence is. Okay, so how does one do that? Now recall that the GE over RT is a function of 4 variables: temperature, pressure, and the number of moles of 2 components. So if I wanted to evaluate the change in N GE over RT, again, I'd say it's a function of TP, N1, and N2. So I could write the following expression. So recall this strategy of we take the partial derivative of our expression with respect to each one of the variables while keeping the other 3 constants. This is what the first term looks like. Taking the partial derivative of my term divided by, or with respect to temperature first, keeping the other 3 constant, and then I just cycle through the variables. So try and derive that. So that's the equation. Oh, and actually I forgot, you have to multiply by dt. You have to multiply by the variable that you are taking the partial derivative with respect to. So dt, dp, dn1, and dn2 there. All right, simplifying this expression, I can say that in the last 2 terms, this dng over rt with respect to n1, that is literally the definition of the activity coefficient. That is ln of gamma 1. So ln gamma 1 is there. ln gamma 2 is there. That should be in your notes from Friday. So that takes care of simplifying those 2 terms. And now in the first 2 terms, we've got some constant variables that we can take out of the partial derivative. So in the first term, I've got N1 and N2 being held constant, and therefore this N is constant as well. R is the gas constant, so that is always constant. So I can take out an N over R from there and say this is dGE over T by dt, constant P N1, N2 dt. All right, so all I did is I pulled out an N over R because those two things are constant. In the second term, I can pull N, R, and T out of this partial derivative because I've got T being held constant as well. It's a partial derivative with respect to P. So it's N over RT dGE by dP at constant T, N1, and N2 times dP. All right, so I've simplified those four things. And before I clean it up a little bit, I want to make some more simplifications here. I've got a fundamental property relationship that takes care of this dGE by dP at constant T. So recall the fundamental property relationships. I can say that molar excess volume is equal to the partial derivative of excess molar Gibbs free energy with respect to temperature at constant T. So I can simplify that. And then I've got a little bit more complicated of an expression to take care of this one because it's partial derivative with respect to T. However, T is in the expression itself. So here I'll need the quotient rule. So by the quotient rule, remember it is the derivative of the top, which is excess molar Gibbs free energy as a function of temperature, but again, we don't necessarily know what that function is, so we can't evaluate the integral completely. So just to write it a little neater, I'm going to say, just evaluate what the derivative of this expression is. dGE over T with respect to T by quotient rule is the derivative of the top, so that is dGE with respect to T times the bottom function, which is just T, minus the derivative of the bottom function, which is 1 because it's the derivative of T with respect to T is 1, times the top function, which is excess molar Gibbs free energy, all divided by the bottom function square. Now we can evaluate what the partial derivative of Gibbs with respect to temperature is, and this all keeping constant P, N1, and N2. There's another fundamental property relationship that says this is equal to entropy. All right, so I can plug that in as well. So this partial derivative is equal to minus T minus T excess molar entropy minus molar excess Gibbs over T square. All right, I've got stuff going all over the place, so I can now simplify things a little bit. Actually, one quick correction, minus SE. So that's where this minus comes from down here. Also, I've got minus G minus TS, and I can say that excess molar enthalpy is GE plus T excess entropy. All right, because that's just the definition of enthalpy, because G is equal to H minus TS. G is H minus TS. That is the definition. So I can expand that by just rearranging and using the excess properties instead. So I can replace this by a minus enthalpy, different color, minus HE. All right, plugging everything in that I've done so far. I'm going to pause and write it myself. All right, now this equation is something that we can use to evaluate the temperature and pressure dependence. So to evaluate temperature dependence, we simply take the partial derivative of this entire expression with respect to temperature. Take partial deriv with respect to temperature. Okay, seems easy enough. We'll do the same thing for pressure in a moment. So we say dNGE over RT. Actually, I'm going to put this out front. So d dt, like that, right, at constant pressure, N1 and N2. So that is going to equal, taking the total derivative with respect to dt should then give me back 1. So minus N excess molar enthalpy over RT square dt at constant P, N1, N2. And remember, by the rules of calculus, the partial derivative of any variable with respect to that variable is 1. And then for the other three terms, if I take the partial derivative with respect to temperature while keeping the other variables constant, so just for example, I've got NVE over RT, partial derivative of pressure with respect to temperature. But again, if I'm keeping pressure constant, then any partial derivative, the change in a variable, if I keep that variable constant, has to be 0. You can see the same thing for N1 and N2. So I'll write out N1, but then I won't write out N2. So partial derivative of N1 with respect to T, keeping P, N1, N2 constant, because I've got an N1, I'm measuring the change of N1 while keeping N1 constant there. This is 0. Same thing for the last term. So my final expression for the partial, or the change in this quantity, which is what my model is. So the change in excess molar Gibbs free energy over RT. Shouldn't have had that there. Got one too many parentheses now. Okay, just like that. So again, the change in GE over RT with respect to temperature is now simply just this term, minus NHE over RT square. All right, so this is measuring change in GE over RT upon a change in T. All right, let's do the same thing for pressure. To evaluate, I'm going to skip a little bit. And just by following the same logic to evaluate the pressure dependence, now the second term is the only one that stays. So I've got a NVE over RT. And in both of these expressions, if N1 and N2 are held constant, then I can pull this N out of the derivative and cancel it as well. So that's just a simpler version of it. Now, if I were to actually evaluate these two expressions with some experimental numbers, I'd need to have a value handy for the excess molar enthalpy. So I need to know what this is, and I need to know what excess molar volume is. And usually, if you plug these numbers in and you look at the order of magnitude, effect of T is often greater, much greater than the effect of P, than effect of P. So what this means is usually if you want to model at a different condition, you typically don't have to take into account pressure changes, but you might want to take into effect temperature changes. So you may want to see what the change in temperature is by using that equation. So if P changes, what this means practically, use same error, assume that the activity coefficients don't change. Activity coefficients. And if T changes, account for it using this equation. For it with this equation. All right, that will wrap up this video.